Hey, today I will be presenting the paper Nested Diffusion Processes for Anytime Image Generation for the WACV 2024 conference. Diffusion models are the state-of-the-art image generation method today. They can generate impressive-looking photorealistic images using simple text prompts as well as adapt to many downstream tasks. At the same time, diffusion sampling is a long iterative process in which the user must wait for the process to terminate before being able to see the results. The diffusion sampling process has a sequential nature. During inference, we start with white Gaussian noise and iteratively predict the clean image, which is combined again with the noise in preparation for the next steps. An interesting question is what would happen if we stopped the generation process in the middle? Would we be satisfied with the image last generated by the model? Would we be able to tell if we should discard this generation sequence based on the current output? A solution to these questions would be a generation algorithm that can be stopped and resumed, in which the intermediate steps are meaningful. Such an algorithm would be an anytime generation algorithm. Going back to the DDPM algorithm, noisy versions are sampled iteratively from the model distribution P of xt minus 1 given xt. To see the problematic nature of this approach, it is instructive to reinterpret the sampling from P of xt minus 1 given xt as a two-step procedure. We first sample x0 given xt, and then we sample xt minus 1 given x0 and xt. This reinterpretation can always be done regardless of how we choose to model p of xt minus 1 given xt. This sampling technique is possible due to the probability rule of sampling from a joint distribution. We begin with sampling b from p of b, and then we sample A from P of A given the sample we already have of B. Our sequential sampling interpretation can be viewed as a marginalization. P of xt minus 1 given xt, the distribution of the next diffusion step, is sampled by first sampling x0 given xt using the DNN approximation, and then using a closed form distribution Q to go from xt and the x0 that we have sampled to xt minus 1. Our interpretation reveals that the specific choice of P of xt minus 1 given xt used in DDPM corresponds to the step of sampling x0 given xt being deterministic. Applying the DNN approximation can be seen as sampling from a delta distribution that is centered around the conditional MMSE estimator. Interestingly, with this interpretation, we wonder whether the conditional MMSE estimator is the best choice for this DNN approximation. After all, we know that the conditional mean is a blurry image and is not a very good representative of x0. What if, instead of a conditional mean, we could approximate P of x0 given xt using a complete generative model? And given that the best generative model we have is a diffusion model, let's approximate P of x0 given xt with its own diffusion process. This idea is the essence of nested diffusion. In nested diffusion, instead of sampling x0 hat using one evaluation of the model, we use an inner diffusion process to sample x0. So, while a vanilla diffusion process is a sequentially progressive from highly noisy samples to a clean image, nested diffusion has two nested loops of progression, where each step of the outer process uses a complete inner diffusion process containing several inner denoising steps. The algorithm for nested diffusion is presented here, with the outer diffusion in blue and the inner diffusion in red. As you can see, it is formed with two nested loops, where each of them performs a diffusion process. Nested diffusion has a predefined number of outer steps, each of which can use any number of inner steps for its approximation of x0. Notice that only the inner diffusion process uses the deep neural network. Therefore, computational cost of applying nested diffusion is measured by the amount of neural function evaluations, or NFEs, in the inner process. Sampling from the known distribution Q is computationally negligible. Nested diffusion sampling algorithm has the advantage of being an anytime algorithm because the result of each inner diffusion process is a clean image sampled from P of x0 given xt. Stopping sampling during the generation algorithm would leave us with a satisfying image. Let's see what this looks like. In this example, we compare vanilla diffusion process with nested diffusion. We use the same DNN model and the same number of NFEs. Therefore, sampling time is equal for both methods. At the beginning of the sampling process, vanilla diffusion yields blurry predictions which match the conditional mean of the DNN model applied. For the same computational cost, nested diffusion returns a clean image. With the accumulation of more steps, vanilla diffusion's intermediate predictions start to show detail, but remain blurry. At the same time, nested diffusion produces crisp images. At the end of the sampling process, both methods produce pleasing images of comparable quality. We can see that the progression of FID during the sampling process for both algorithms in this graph. Vanilla diffusion produces intermediate predictions that do not resemble real images for most of the sampling duration, resulting in high FID scores. Nested diffusion's images correspond to the predictions at the bottom green line, which has low FID scores throughout the sampling algorithm. The cyan line corresponds to the intermediate predictions of the inner diffusion processes, each of which has progression from low-quality predictions to high-quality samples. If terminated prematurely, nested diffusion would return an image from the last outer step, shown along the green line, to ensure that a satisfying sample is always returned. We notice that the final FID score for both algorithms is comparable at the end of sampling. Here are several examples for images generated with a DIT algorithm for ImageNet class conditional generation, comparing vanilla diffusion and nested diffusion generations. The diffusion processes progresses from top to bottom following the NFE notation. Here are additional examples. Nested diffusion can also be extended to many various sampling methods used with diffusion models. In this slide, we show nested diffusion algorithm can work with stable diffusion DNN, which utilizes both latent diffusion and text conditioning for generation. The diffusion here progresses from left to right. Nested diffusion can also be extended to more complex samplers that combine diffusion steps with additional conditioning. In this example, we show inverse problem solving using nested diffusion and DDRM. In our quantitative comparison, we show that for many types of generation and different choices of numbers of steps, nested diffusion greatly improves intermediate prediction quality, corresponding to the anytime generation property, as well as retains comparable final image quality. Beyond the anytime generation property, nested diffusion can be used to enhance the interactivity of generation. In this example, where multiple images are produced in parallel, a user may select the preferred sample at the end of each inner diffusion process to fine-tune the generation in the desired direction. This can be taken a step further by changing the text prompt or even the model used for generation during different steps, enhancing control over the sampling process. We make our nested diffusion code available on GitHub. You're also welcome to try nested diffusion on the Hugging Face space based on the Stable Diffusion text-to-image model. Thank you for listening.